In example 4, we're looking to apply the first derivative test in table format again to the function. This is g of x equals x to the 2/3 times 4 minus x. Okay, verify the results graphically. So the first thing to do is discuss this function's domain. So the domain of the function would include any restrictions to the domain values that were not able to be plugged in. Because the denominator of x to the 2/3 is odd, it's a cube root that got squared, but cube roots don't have any domain restrictions. You can plug in negative values or positive values. So the domain of this function is going to be all real numbers. There are no domain restrictions for an odd denominator power. Again, this part's polynomial, this is not polynomial. I can't use the polynomial as a reason. It's not a polynomial, but because the denominator is odd. Okay, so that's my reason power denominator is odd. Second, after I find the domain, I just want to find the derivative. This is going to require the product rule. I have a product here. So let's do the derivative of x to the 2/3 first. So we have 2/3 x to the, subtract 1, so negative 1/3. Leave the 4 minus x alone, plus the reverse, leave the x to the 2/3 alone, times the derivative of 4 minus x, which is negative 1. And if we simplify this, this is 2 over 3 x to the 1/3 power. Let's go ahead and put our 4 minus x in the numerator as well, just putting the 2 and move that bond to the bottom because I had a negative power. Then we have minus x to the 2/3 power. Okay, so I'm going to want to, in step 3, look for the critical values. That's going to involve us setting the derivative equal to 0 and locating where it fails to exist. G prime of x equals 0, and g prime of x fails to exist. I like to do where it fails to exist first so I don't forget to do it. Oftentimes we'll set the derivative equal to 0 and think we're done when we're not. So where it fails to exist. Last time I didn't have any places because it was polynomial. This is not polynomial, and since it has a denominator, I can have it fail to exist any place where the denominator is equal to 0. So denominator equals 0 gives us 3x to the 1/3 equals 0. Divide by 3, that's x to the 1/3 equals 0. Cube both sides, you get x equals 0. So x equals 0 is one place where the function fails to exist. I'm going to underline that right now as one of my critical values. I should get a few more critical values by setting the original function, derivative function, equal to 0. So back over here, we have our 2 times 4 minus x over our 3x to the 1/3 minus the x to the 2/3 equal to 0. If I add to the other side, 2 times 4 minus x over 3x to the 1/3 equals x to the 2/3, and then multiply both sides by the denominator. 2 times 4 minus x equals 3 times x to the first, because 1/3 plus 2/3 is 3/3 or 1. And then distributing, we have 8 minus 2x equals 3x, so x, add that over, you have 5, divide by 5, you have 8 fifths. So x equals 8 fifths. Okay, again, I can write my extra step in here, that's 8 equals 5x, and then divide by 5. Alright, so we have critical values. There are 2 of them. We have 8 fifths and 0 as our 2 critical values. One was found by setting the derivative equal to 0. One was found by finding where the derivative fails to exist. Now we're going to go into a table using the first derivative test. The first derivative test is this table. So when I use the first derivative test, I make test intervals. I choose test values. I look at the sign, and I look at the interval being increasing or decreasing. Okay, so the domain was originally negative infinity to infinity on this function. I partitioned that in 2 places. So we go from negative infinity to the smaller value of 0 Then we're going to go from 0 to 8/5. And finally, we'll go from 8/5 to infinity. Okay, two critical values, so two partitions of the domain. Taking two breaks gives us three intervals. Test values. Pick something less than 0, so I'll choose -1. Pick something between 0 and 8/5. 8/5 is larger than 1, so I'll pick 1. And pick something bigger than 8/5. Again, I'll just pick something arbitrary like 10. It happens to be bigger than 8/5. Now I want to plug those into the derivative. Remember that I'm taking these test values and plugging them into the derivative. Test values into the derivative to find the sign, not into the original function here, into the derivative. Okay. So our derivative up here, I'm going to find it, there it is, plug in -1. Okay, I'm just looking at sign here. So when I plug in -1, I have I have 4 minus -1 is 5. 2 times 5, plug in -1, that's -1. So this whole thing becomes negative. It's negative something. Maybe it would help to get an actual value on this, because I'm going to subtract 1. It's going to actually still be negative, but I'll get an actual value just for making this a little bit easier. So I've got my negative. If I go into Desmos, I can do this two ways. First of all, I could just type in the derivative, f of x equals, and my derivative, which was 2 times 4 minus x, divided by x to the 1/3 power, minus x to the 2/3 power. So I evaluated this at -1. I don't need the number, so I didn't actually calculate the number as -11. I just need to know that it was negative. Okay, I can do that again. F of 1, that one's positive, and then f of 10, that one's negative. Okay, so back over here, I can fill in that I had first a negative, then a positive, then a negative. One other way that you can do this if you are feeling like it is, instead of typing in the derivative, if you want to just check yourself, you had to find the derivative anyway, but if you want to check yourself, you can type in the original function, x to the 2/3 times 4 minus x, and then you could evaluate the derivative g prime at those values. Thank you for noticing I just didn't put the 3 up here. It hopefully doesn't change too much, but it does change the last one. There we go, put the 3 in the correct spot now. Okay, so I had the right signs, but I forgot the 3 from the derivative when I typed it in, so that could have been unfortunate here. But now I can confirm that I have my derivative entered correctly, so if I could do the g prime of the rest of them, it should work out just fine. G prime of 1 and g prime of 10. Beautiful. Okay, so typing in the derivative, as long as you type it correctly, is going to be even more efficient, but I can also type in the original function and evaluate the derivative. Good to have two options. Alright, back to our conclusions. Because this was negative, positive, negative, I know that this negative means that the function was decreasing on the interval, positive means that the function was increasing on the interval, negative means the function was decreasing on the interval, and I can get our conclusions about increasing and decreasing. So the function is increasing on the interval 0 to 8/5, and decreasing on the intervals -infinity to 0 and 8/5 to infinity. Okay, so again, that's my conclusion to step 4 about intervals of increase, decrease. Then step 5 is going to have us classify the extrema based on the changes. All right, so we have decreasing to increasing. So decreasing to increasing, that one's going to be a minima. Then we have increasing to decreasing, so that one's going to be a maxima. Okay, so there is a minima at x equals the x value of 0, and there's going to be a max at, and again these are local, x equals 8/5. Okay, now looking at my graph, I'm going to confirm this. One additional point of information I have is that the derivative did not exist here at 0, so this one was going to be sharp. The derivative did exist and equaled 0 at the 8/5, so this one was going to be smooth. Putting all of that knowledge together, it should match my graph. I have a sharp minima at 0, I have a smooth minima at 8/5, and I have decreasing between -infinity and 0, again decreasing from 8/5 to infinity, and increasing between 0 and 8/5. Confirmed.